Hello everybody! I hope everyone's having a wonderful day. So today we're going to be proving the so-called smoothness rule. So this is one of these lovely properties of so-called smooth functions. So I have a proper video that explains more about smoothness. You could check it in the relevant materials, probably in the description. First I want to state what the smoothness rule is, just so that we're aware of it, because we're going to write out the proof for this. So, or at least a proof for this. So let there be two complexity functions f and g. So I want to assume that f is big O of g, where an input n is a power of some integer constant b greater or equal to 2. So for example, if n is a power of 2. So it'd be like n is 1, 2, 4, 8, 16, 32, and so on. So I'm going to assume there's some restriction on the input. So if f is asymptotically non-decreasing, which might I add, remember, this means that there exists a positive integer, n, like you could call it n0, whatever it might be. There's a sufficiently large n such that f of n, if f is asymptotically non-decreasing, f of n is less or equal to f of n plus 1 for all points of that sufficiently large n and after. So if f is asymptotically non-decreasing, or some people call this eventually non-decreasing, and g is smooth, then you could say that f is big O of g unconditionally, so without needing to quantify what n is. So as long as, so it's for all n, so it propagates across all the values of n in the domain. So like I said during the talk I've done on smoothness, you could use this, actually, this greatly simplify your analysis. So this is oftentimes the case in algorithms, algorithm analysis for divide and conquer algorithms, but I've shown you other examples, such as trying to simplify the analysis of proving harmonic numbers are in fact logarithmic in their asymptotic behavior. So I've talked about this in other videos, so do check those out if you're curious. Today I'm just going to be writing out what the proof is for this. So a proof, and this proof uses a property that we proved actually in another part of my series, where we've shown that actually all smooth functions are actually what they call B-smooth. So this is actually a vital part of this proof. So I'm not going to write it down here, but you'll see it in my proof. So what I'm going to do is I'm going to first outline what I'm going to do. So I'm going to invoke some properties of f, and then I might do some stuff with g. And then I'm going to put everything together with some inequalities. This might look very familiar to you if you've seen another proof I did involving smoothness, in fact, B-smoothness. So I'm going to use a technique that's very familiar from over there. So I'm going to say function f of n is big O of g when n is a power of b. So what? What does that mean if this holds? We just use the definition of big O again, right? So there exists constants. There exist constants, C. I'll call them C1 and N1. Now, is C a positive integer or a real number? It's a positive integer. No, it's a positive real number. Correct. Yeah, it's positive real number. And n0, which that's the positive integer, such that for all n greater or equal to n0, is it n0 or n1? Let's call this n1. I'm going to use this as setup. For all n's greater or equal to n1. Remember, when I write down n here, that n is a power of b. So keep that in mind. It's going to come up later. So just as a reminder, remember, n is a power of... So remember, n is a power of b. So just remember that in this statement. This is why you have to be very careful when you read statements like this. N is a power of b. Then we know that f of n is less than or equal to c1 times g of n. Now I'm going to say something about g. Next, function g is smooth So I'm going to use the property that it's B smooth, implying G is B smooth, where constants C2, I'm just going to C2 and 2 exist, and G of Bn is less than or equal to C2 times G of n for all n greater or equal to n2. That's just me using the definition of B smooth. You might ask, Dan, where does this come from? Remember, this is the second condition of B smoothness. So of what means to be smooth? So not smooth, but be smooth, okay? So just follow me here. So in smooth, this is just 2. In B smooth, it's B. So I have these two pieces, but I also need to note that F and G are both asymptotically non-decreasing, right? They have to be. That's part of their definition. So I'm going to need some more constants to play around with. Both F and G are asymptotically non-decreasing. So I'm going to use the definition of that, asymptotically non-decreasing. And I'm putting parentheses, I'm going to remind you that as G is smooth, because some people forget that smoothness implies that it's asymptotically non-decreasing as well. So there exists, so I'm just going to use the definition of asymptotically non-decreasing. So there exists n3 and 4, which are both going to be positive integers. So I'm going to invoke it twice, just chain them together. So remember, in asymptotically non-decreasing, that means that there exists a constant such that the f of n is less than or equal to f of n plus 1, if I was talking about function f. So there exists n3 and n4 such that both f of n is less than or equal to f of n plus 1, and g of n is less than or equal to g of n plus 1 for all n greater or equal to n3 and n greater or equal to n4, respectively. So that's the setup. So all I've done is so remember, don't make it look way complicated than it actually is. So all I've done is I've stated what the condition of the theorem is. Then I invoke the fact that being smooth means it's B smooth. And then I use the fact that it's asymptotically non-decreasing, which would imply that there exist two constants, one for each function. And that's how I get n3 and n4 from. So there's 4 constants for n's kicking around, and there's 2 c values. Can you see why in some of my other proofs I try to avoid having a lot of these constants? Here you're going to see it's very slick if I do it this way. So let's get over to this board over here. So let's do that. So what we're going to do is I'm going to pick n0, and then you're going to see how, so this is going to be one of the few examples where you're really going to see me pick an n0 first, and then I'm going to pick c. You'll see why I pick it in this order. Like I said, you don't have to pick c or n0 in a particular order. It's just, sometimes it's more convenient to do it one way, and other times it's convenient to do it another way. So I'm going to pick, now prepare for yourself for this. So I'm going to pick n0. So remember, this is the one that we need for the big O statement. So this one over here. So that's the one I want to use it for. So this is going to be the c and n0 for that statement right there. So I'm going to pick n0 to be the maximum of the following: n1, n2, n3, n4, and b. Now b is a constant, so I'm going to be allowed to use it. You'll see why I'm going to use it. It makes it easier to argue what I'm going to say. So of all these 5 constants, which is a lot if you really think about it, I have 5 constants here. I'm going to select the largest one to be n0. Then I want you to observe. Then observe that for any n greater than or equal to n0, which, might I remind you, is also greater or equal to 1. I just want to remind you of that fact. Remember, n0 has to be positive. There exists integer k greater or equal to 0 such that the following is always true for such an n0. So like this will always exist for such a selection here for n. So it doesn't matter that n is a power of b, it's just that it's always going to be holding as long as this is the case. Such that b to the power of k is less than or equal to n. So you might ask, Dan, where did this come from? Now imagine if n was in fact a power of b. You'd agree with me that I could write this as like an equality, right? But it might not be the case that n is in fact a power of b. So it might be slightly smaller than 1, or it might be closer to the other one, the next highest power of b. But you would agree with me that if this, you'll definitely be able to find this n. Well, you'll be able to find a k. I should be more precise. Remember, there exists this k such that you can get, there's a gap between these two. So I have b to the power of k plus 1. So between these two exponents, this is why the b has to be, in fact, bigger than 1. Otherwise, you wouldn't be able to create a gap like this. Which, now you might ask, okay, well, what am I going to bound this by? I'm going to bound it by b times n. Now, you might ask, Dan, why is that true? Well, think about it. It's b times b to the power of k, right? Well, what's b times b to the power of k? Well, we know that b to the power of k is less than or equal to n, right? But we also know that this is indeed larger than n. But this is b times something that is, it's not going to definitely be more than n because it is in fact n, right? So you know that this bounds on that side. So I know I'll definitely be able to bound from above b to the power of k with n. So I'm going to have n times whatever the extra factor here would be, b, right? So that's where b times n comes from. That's why I want to put b in here, just to make sure that b is, the constant is large enough. Makes it a little easier to read the argument. So I know that this k will always exist such that I could sandwich it between n, regardless of what n is. Remember, n doesn't have to be a power of b at this stage. It only is in that first sentence I made in the proof here. And now we're going to, now this is where you have to follow me very carefully. Now f of n is going to be less than or equal to the following. It's going to be less than or equal to b to the power of k plus 1. Now you might ask, Dan, why is that true for f? Now remember, f in the statement of the theorem says that it's asymptotically non-decreasing. That means if I put in a larger value for the input, it's either going to be equal to the ones that have lesser value, or it's going to be larger. So this it's just, I'm invoking this relationship that n is less than b to the power k plus 1. So I'm just saying f is asymptotically non-decreasing. So that's the fact I'm using here. Now next, we know the following. You would agree with me that b to the power of k plus 1 is in fact a power of b, right? It's a power of b. But what do we know about that? We know that f of n, for when n is a power of b, is less than or equal to c1 times g of what? G of n, when n is a power of b, right? But this is a power of b, so I can write this. c1 times g of b to the power of k plus 1. Piece of cake, right? So I'm just invoking that I know that f of n, I'm just invoking that f of n is big O of g of n when n is a power of b. That's all I'm invoking here. Piece of cake. So what are we going to do here? Well, remember that G is also asymptotically non-decreasing. And I've picked n0 to be large enough so that I could just simply rewrite it like this. C1 times G times B of n. Sorry, G of B of n. Now this is because G is asymptotically non-decreasing, right? Why? Because remember, b to the k plus 1 is less or equal to b times n. Like I said, piece of cake. I'm just using all the setup I have over on the left board here. Easy stuff, okay? So this isn't too bad. So all I've done is I've jumped. So did you see how I've jumped from a power of b down to this? But this should look very familiar to you. This should look like something about smoothness, right? Well, what do I know about this right here? I know that a function that is smooth, so G is smooth, but that means it's also B smooth. But what does that mean? Well, that means that G of B of n, well, G of B times n, is in fact big O of G, right? G of n. That means that there exists that other constant C2. So I have C1 times, do I put G here? No, right? I put C2 right here times G of n. This is just me invoking the fact that G is smooth. If you really want to be precise, it is B smooth. So that's just me using that portion of my setup that I have over on the left board. Like I said, I've set up everything so I can line up all the inequalities nicely here. But you might ask, okay, well, what is that? So now this is equal to C1 times C2 times G of n. So do you see what I could pick for C now? Well, did you see it? So now I have n0. What should C be? Well, now I have that f of n is less than or equal to C1 times C2 times G of n. What should C be? Maybe this should be C. Do you see now? We've actually just showed that f of n is less than or equal to C times G of n for all n greater or equal to n0. Notice there's no more anymore that n is a power of b. This is true regardless of what n is, as long as n is a valid domain, part of the domain of the original function. So now I don't have that restriction in place. So all I have to do now is just select C is equal to C1 times C2. Therefore, C and n0 have been, the have is sort of melting there, have been selected, been selected so that, for all n greater or equal to n0, f of n is less than or equal to C times G of n. Therefore, just to really put an exclamation mark on this, I'm using therefore twice. If you're writing this more standardly, you normally put like thus or hence or something. I just felt like having a little fun here. Therefore, f of n is, f is big O of G unconditionally. So it means unconditionally here. And we're done. Boom. Piece of cake. So remember, the whole idea here is I created some setup here where I invoked each one of the definitions to get constants, all those different values for C, and I had different values for N0. And then I used those by selecting N0 appropriately so that I can invoke this property where I use the asymptotic non-decreasing property of the functions to chain together some inequalities that relate a power of B to the next power of B, so I could put n in between there and sandwich them, plus chain these inequalities together based on those definitions. So it's really not too terribly bad if you really just break this apart and analyze it carefully. So if you're really just unsure about some parts of this, such as this, I recommend plugging in certain values for b and k just to convince yourself at first, and then you should really see quite clearly that when you pick n0 to be like this, and the one thing that will really help you is making sure that, remembering that n0 is at least b, that'll hopefully help justify this for you. So that being said, I want to say thank you very much and have yourself a beautiful day.